So welcome everyone to a new episode of our YouTube series of seminars of the Quantum Energy Initiative, where we let researchers present their work on about studying quantum energy and how this relates to thermodynamics and quantum engineering and the development of technologies. We want to build metrics to estimate the energetic cost and the physics of quantum technology in an objective, scientific way. We try without trying to sell anything. Today we have Krissia Zawadzki from the University of São Paolo in São Carlos, and she will present us her work about many-body effects at work, scaling up quantum thermodynamics. Krissia, the stage is yours.
Hey, hello everyone. I'm very pleased to be here today. It's such an honor to give a seminar to the Quantum Energy Initiative. I'm a big fan of this community. I'm looking forward to join the community and bring new enthusiasts from Brazil, the youngest generations in quantum thermo. And as the title of my talk suggests, the topic that I picked to talk to you today is this research program within the field of quantum thermodynamics, which is focused on studying quantum many-body systems with this long-term desire to develop a scalable and efficient quantum technologies. And I was brought to this field of quantum thermodynamics. This is a research program, and I'm really pleased to be introduced to this field by Irene D'Amico, who is here in the audience, and I should thank her as the main character responsible for me being here today. And she was the person who opened my eyes to admire the beauty of quantum thermodynamics and introduced me to this amazing network of collaborators who are featured here and who were part of all the results I will show you today in this during these minutes I have. So beyond Irene, at the time we collaborated, we are still collaborating, but at the time I was a PhD and in my first postdoc, we did a lot of works with Amy Skelt in New York. She was a PhD, Irene supervised. We also collaborated a lot with Roberto Serra from the Federal University of ABC and Marcela Herrera, now in Colombia, at the Autonomous University of Colombia. And they had amazing results, both in experimental and theoretical quantum thermodynamics. If you ever come to São Paulo, I really invite you to go to see Roberto's lab for quantum thermo using MRI. It's amazing. Professor Vivian França from Unesp is another state university in the state of São Paulo. She is an expert in entanglement in many-body systems, and at the time she also volunteered. Actually, she invited Canela, her PhD student, to study this business of the role of entanglement in the work statistics is one of the results I will be discussing today. Also, the crew from Dublin, Steve Campbell and Anthony Keel, amazing people. Really enjoyed my time there in Dublin collaborating with them. And together with Professor Gabriel Lange, now in Rochester, we studied the effects of a finite-time dynamics and the consequences of shaking a many-body systems at finite time. And no less important, two collaborators of mine, which are two cute little ones, which helped me a lot within my journey, are my two cats. And I think I should add them as my collaborators as well. And thanks to all these nice people, I'm currently based in São Paulo, at the University of São Paulo in São Carlos, as a professor. I was hired as a faculty last year. And before you ask, where are you based? So this is a map of Brazil. So this huge country, the state of São Paulo is here. Here you have the capital, and this is
Sorry,
all the
Krissia.
camp.
Sorry to interrupt. I don't see the slide moving.
The slide is not changing. Oh my
Yes.
God. Sorry about that.
It's
And I
okay.
was in full screen mode.
Yes.
And I don't know. Now it is. Cool, cool. Oh,
No,
and I was
Actually,
it's
no, it
pointing
not.
doesn't
and
go
it's
full screen. I
so,
think
and you
you're
didn't see,
capturing,
oh,
you should capture the whole screen. Probably you're capturing only.
that's weird. Okay, so I think I will keep, okay, so I will share
Try.
another, yeah, I will
Yes.
use a different app. Otherwise, let me share another one. Okay, so we'll use, you didn't see my cats. That's such a shame.
No. Such a shame. Yes. Okay.
Now you see, yes. So
Now,
yes,
Yes.
so
yes,
these are
exactly.
all my
Exactly.
network of collaborators, including my
Nice.
cats. Thank you for letting me know. Okay. So, okay, so thanks to all these people, I'm based now at the University of São Paulo as a faculty. So this is a map of Brazil. This is the state of São Paulo, as I already told you. This is the capital. USP has many campi spread all over the state. Here is São Carlos in the middle of the countryside, and here is, we don't have the beach, we don't have a coast, but we do have the brigadeiros. These are the Brazilian truffles, the chocolate truffles made out of condensed milk and cocoa powder, which inspired the name of what will be my group in the future. Cocoa meaning quantum correlations and applications. I need to find an acronym. And I really should thank all the creative people who gave amazing names for their projects in Europe. So I got inspiration to give this cocoa name to my research group. So here I'm based. And if you ever come to visit me, I can provide the brigadeiros. That's the deal. We don't have beaches, but we do have the brigadeiros, the national delicacy. Okay.
Convinced.
And okay, so now it's time for physics. So this is the menu of my talk. I will start by telling you why I got interested in this field, actually in this research program of studying many body systems from the perspective of quantum thermodynamics. And I will just anticipate to you that this is just this idea that Phil Anderson quoted very well back in the 60s, that more is different, and this idea that many body systems offer some type of quantum thermodynamical advantage was the huge inspiration that I have to start digging into different problems within this field. Then I will discuss all the challenges that we are facing now to try to address, to harness many body effects to obtain quantum thermodynamical advantage. Then I will show you that there is hope. We can simplify them more using approximations. And this is a research line which was also started with Irene. And then I will share with you some thoughts and reflections on what we need and maybe how we can combine the different communities within this huge field of quantum sciences to try to address this question of building scalable quantum and efficient quantum technologies. Okay, so let's start. I don't think I have to convince this audience that we live in the era of quantum technologies, and we are many promising results have been obtained so far. We currently have different architectures for the quantum computer, some of which were still being debated, right? Topological qubits and Majorana one. But for us to really be able to build technologies that will provide us advantages, not only technologically, but as a society, we need them to be scalable for sure. We need to be able to control them very well and not less efficient. And I think this is very aligned with the purpose of this initiative. We want them to be efficient. And to tackle all these three challenges, scalability, controllability, and efficiency, we are very tempted to study many body systems in such a way that we'll be able to manipulate and control entanglement. because controlling entanglement is the key for us to harness quantum advantage, right? But when we scale up the system, things got really, really complicated because we not only have to take care of the all unwanted effects of the environment, which per se is a huge and massive many-body system, but also internally, the quantum particles we want to manipulate to make them offer us capabilities for sensing, for communication, and even for information processing. This, say, work substance that we want to manipulate can be very complicated and a many-body system as well. So for us to build, say, practical applications of quantum thermodynamics, we need to be able to understand how to manipulate entanglement internally, suppress external errors, and this is essentially a many-body problem of many quantum particles out of equilibrium. And if you are a person with a many-body background, as I was when I was a PhD student, if you want to start addressing this problem very naively, as I was, I'm still naive, but when I was a PhD, I was very naive. The first thing you want to do is, of course, you start to consider a many-body system is still simple enough in such a way that you can still handle it, is still manageable. And we love many-body, condensed matter physicists love spin chain. So this is the first thing that you will be doing to address the many-body complicated system. You consider spin chain, you quench them out of equilibrium, and you see what happens. And this was, in fact, something that Alessandro Silva did back in the early days of quantum thermo after the 2000s. Is studying the so-called work distribution that I will tell you more in a few minutes. I will discuss it in more details, but he was studying what happens with this object, the quantum work distribution, when you take a one-dimensional spin chain, which has a quantum critical point, and if you quench the system across the critical point, you can use the work distribution to somehow quantify how far from equilibrium you are. And in fact, he found very interesting results. I think this is a plot that came from his paper. So this distribution gives you work and work fluctuation. So he showed that both the first moment of this distribution and the second moment associated with the variance, when you cross the critical point is here in G naught equals to 1, it displays this interesting behavior, showing that before the critical point, you have a lot of work, you have less fluctuations, but after you cross the critical point, you have a lot of fluctuations and you reduce the work. Following this work, many other groups started to study quenched many-body systems from the perspective of quantum thermodynamics, specifically focusing on the work distribution, and many interesting results were found. Of course, this was just the starting point for this business of many-body systems and quantum thermodynamics, which inspired not only the study of the work distribution itself, but also these many-body systems as a work substance to build what? For instance, heat engines. And this was very interesting because then back in 2016, in this NGP, it was shown this idea of supremacy of many-body heat engines. Meaning what? Meaning that if you build a thermodynamical cycle using a many-body system composed by many quantum particles, composed of many quantum particles, and then these are the work substance. If these particles, they are correlated with each other, they show that the efficiency is way more increased, much larger than if you have the same working fluid with the same amount of particles, but those particles do not interact with each other. So this was opening the way for this idea of more is different and thermodynamically advantageous, and also following this seminal work by Jaramillo and colleagues, many other groups study proposals of theoretical proposals of building quantum heat engines and batteries, refrigerators out of many body working substances, and demonstrating that in fact you can have advantages even in the efficiency as an engine, or even you are able to store more energy if those particles interact with each other. And these are all theoretical works studying paradigmatic models from condensed matter physics as a way to kind of grasp results of many body advantages. And 2 years ago, a couple of years ago, but last year, this was an experimental attempt to build a many-body heat engine using a cold atom platform. It was a massive collaboration involving groups from Germany, Japan, and Spain, and they were able to show this very, very interesting and remarkable experimental results in which you can build a kind of Otto cycle which is fueled by the change in the statistics of quantum particles. So basically you change the statistics of those particles from bosonic to fermionic, and then you can basically do expansions and compressions, bosonization and fermionization. And they implemented this in the lab. This is a very promising scenario for us to finally try to address using the advantages of many body effects thermodynamically. Of course, in these platforms, everything is extremely well controlled. They are not meant for us to build a tiny device for quantum technologies, but it's an amazing playground for us to test ideas of toy models and then get back to the materials, to the devices, and then start building these devices in a way to apply practical applications of quantum thermodynamics. This is very remarkable. This makes us very excited. But then, okay, I already told you that most of these results were conducted using toy models, let's say well-behaved toy models. But if you really want to get back to reality and address all the effects of the environment, the complications of the particles, the fact that those particles out of equilibrium behave in a very complicated way, yeah, we are not in a very optimistic position anymore. Because now, as I already told you, you have to deal with a very complicated many-body system with a very intricate internal entanglement structure, which will be shaking out of equilibrium. These correlations between particles will evolve. The size of the Hilbert space for us to deal with the system, even at the theoretical level or computational level, is huge. And then, yeah, we are not in a very good position. And back in the day, more or less 10 years ago, we started to complicate those models in a way to introduce more realistic details to what could be considered a quantum thermodynamical process to be implemented in the lab. So basically, the object that we wanted to understand very well in the very beginning was the so-called work distribution, which is this object that I will tell you a few details about. What happens with this distribution when we shake the quantum particles at finite time? And this gives us a more realistic ways of implementing thermal operations. And we can complicate everything, but then we can have a step back and ask ourselves, this is a very complicated problem. And even to simulate that, it consumes a lot of energy, which is kind of outrageous, right? You're trying to build efficient quantum technologies and you're spending a lot of energy in just simulating these models. Can we get a step back and then try to simplify our approach to deal with these complicated many-body systems? And we have been trying to build approximations to describe thermodynamical quantities, taking inspiration in an amazing tool from many-bodies physics, which is density functional theory. So this will be more or less the ideas I will be discussing here today. First, complicating the more to address more realistic details of thermodynamical process in many quantum particles entangled. And then I will try to simplify them more and try to recover the same quantities, the work, the entropy, using these approximations. Okay, so the first object, which I love, the quantum work distribution. So when we started studying the work distribution, we wanted to understand a lot of things. So at the time, I already show you a few works, and including Alessandro Silva's work, in which he addressed the first two moments of this object, the work distribution. But we have a lot of motivations, a few motivations to start studying the work distribution at finite time using some toy model, but it's a little bit more complicated. But the things we wanted to understand the most were the following. How large my many-body system have to be in such a way that I can kind of recover what I would expect from a classical system? What are the quantum ingredients that play a role in the work distribution? Another interesting thing, most of the results previously for the work distribution focused on the first and the second moment, of course, because the first moment tells you how much work you can extract or inject in a quantum system on average. The second moment tells you how much fluctuations you have, what's the weight of the fluctuations. But we asked ourselves, what about the high order moments? What do they tell you about the shape of the distribution, the finite time dynamics? Is there some sort of information on the reversibility in the high order moments? And we also study the entropy production, because now the system evolves at finite time, and I do not have guarantee that the protocol that I carried out made everything be almost in equilibrium or adiabatically. Okay. So the work distribution, I don't know if all of you are familiar with the work distribution, but long story short, the work distribution is this object that describes how much work you can extract from a quantum system, what are the fluctuations of the work, and also what else happens, because work cannot be considered unobservable. So there is no way that you can measure work directly. A way for you to recover how much work you can extract or inject in a quantum system is to actually carry out a two-point measurement protocol, in which basically you prepare your system in initial state. Then you drive the system. It can be at finite time, but can be also a sudden quench by changing a given control parameter that is responsible for evolving your many-body Hamiltonian. And after you reach your final state, you ask yourself, what is the probability, given that I start within an initial eigenstate of the initial Hamiltonian, what is the probability for me to arrive to a final state of the final Hamiltonian? And if you collect all these probabilities together, now the work assumes the role of stochastic variable, and the distribution gives you all the information that you need to address the energetics of this out of equilibrium process. So these statistics, I already told you that the average give you how much work you can extract or absorb on average. The second moment tells you the variance of this distribution. So the larger the variance, the more fluctuations you have, meaning that you have all these transitions between levels from the initial Hamiltonian to the final Hamiltonian. They are separated a lot in energy. They are not close to each other, meaning that ground state has a non-negligible probability to reach a high excited state of the final Hamiltonian. And this skewness tells you the probability for you to be more on the left side or the right side of the energy. Or I mean, if you are here, it's more probable for you to evolve and reach a high energy state or a lower energy state. So this gives you the asymmetry, and the kurtosis gives you the long tails, the probabilities of the tails of your distribution. But in this first work, we focus on these 3 moments of the work distribution, trying to see what happens now when I have a many-body systems. The number of levels of the initial system, the initial Hamiltonian and the final Hamiltonian, grows exponentially. What happens with this distribution? How it looks like. And another quantity that we wanted to investigate beyond the work distribution, but also related to the work distribution, is the entropy production in this process of driving the system at finite time, controlling a given parameter. Can be the magnetic field, can be an electric field. And we know that if you do a protocol really slow, we are close to equilibrium. So I'm guaranteed that if I start from equilibrium and I do this protocol very slowly, I will end up in another equilibrium state. If I carry out an adiabatic protocol, I'm very close to equilibrium, but it can be that I'm still not that close to equilibrium, not precisely at the final equilibrium state. And of course, if I do a fast protocol, I'm guaranteed to be very far away from equilibrium. And this is a region in which I'm expected to observe quantum friction. And the fluctuation dissipation theorem tells us that the entropy production should be upper bounded by the fluctuations of work. So if I have a work distribution with a huge variance, that means essentially that I produced a lot of entropy, and I want to produce as less entropy as I like. So basically, this was the scope for our first work on the work distribution. And we had to consider an interesting model. At the time, I was obsessed with the Hubbard Hamiltonian in 1D. I was studying the entanglement properties of the Hubbard Hamiltonian, which is one of the most paradigmatic models in condensed matter physics. And it's a very simple model, which basically describes electrons within a lattice, can be one-dimensional or two-dimensional, and they can hop from one lattice side to the other, and the energetic cost for this kinetic energy is J. But these electrons, because they obey Pauli exclusion principle, there is a penalty for sites to be double occupied with electrons up and down at the same site. And this model, even with its simplicity, is very rich because it describes one of the most featured quantum phase transitions, which is the transition between a metallic phase and insulating phase, where the particles no longer can move. So this is the competition between two scales. J tells how much the electrons try to delocalize, and U tells you how much the electrons can localize and stay frozen, and no transport you cannot have transport when you have an insulating phase. This model has an analytical solution using Bethe ansatz, but if you add a simple term here or more terms to this Hamiltonian, for instance, if you add inhomogeneities all over your lattice sites, can be a local potential, this model becomes very, very complicated, especially because the number of degrees of freedom that you need to describe the physics of this model grows exponential with 4 to the L. So if you just have two sides, a dimer, you have a Hilbert space of 4, but if you have an octamer, 8 sides with a bunch of symmetries, even including all the symmetries of this model, the size of the Hilbert space is almost 2000. And why is this interesting? Because we can consider this model and this complexity of the degrees of freedom to address this transition between what could be quantum features and classical features in the work distribution, meaning that how many degrees of freedom should I have to recover a result of a work distribution that is a beautiful Gaussian, as I would expect for a system behaving almost classically. And as I already told you that I need to shake the system, I can carry out a given protocol. I could change J, I could change U in time, but here we decided to pick a work protocol in which it's very interesting because it does what? It does, it creates a different, an electric bias across your lattice. So in our case, it's a one-dimensional lattice, a chain, a spin chain. And then this electric field, what it's going to do to your system, the particles will move. So you have from the low bias to the highest bias, meaning that you create a transport. This electrical field is trying to transport particles across the chain. But at the same time, you have the Coulomb repulsion. And then you can ask, what happens with the interplay between this electrical bias that is trying to transport particles across the chain and this term, the Coulomb repulsion, trying to localize the particles in the same site? How much energy we need to pump in the system through this external drive, trying to create a current if we are in an insulating phase? How much is this going to cost? So this is the setup that we consider, and then we started digging into the quantum work distribution. So here I show you two limits of this model. I told you that when I have U equals 0, if I don't have this external potential, I am in a perfect metallic phase. And if I apply this bias, all the particles are free to move across the chain. These are the dark, shown here as the darker blue. If I increase the Coulomb repulsion, then I enter in this multi-insulating phase. I'm in the very strongly correlated regime. And here I am expected to be able to, actually to not be able to transport any particle across the chain. And then I can ask what happens with the work distribution. So this is, here I show you the distribution for 4 sites. When I drive this protocol, I create this bias 4 times sufficiently long, for sufficiently long times, because tau here is the scale that sets the speed of my drive, meaning that if tau is large, I'm doing this protocol slowly. If tau is small, I'm doing this protocol very fast. And this is the plot for 4 sites. The Hilbert space is of the order of 36, meaning that I will have up to 36 squared transitions entering in my work distribution. And what I see is that when I am in the metallic phase, my distribution is populated with a lot of possible transitions. And as I enter the insulating phase of my system, I cannot extract any work from my system. My system is insulated. And so if this is a very sharp peaked distribution. When I enter, this is U of the order of 10. So we see this crossover from, it's not Gaussian, but I will show you in a minute that if I increase the system size from a Gaussian distribution to a peaked distribution. So this was supposed to be an animation, but in this preview it is not going to work. But here's the distribution for 8 sites. For U equals to 0, so the non-interacting regime, I observe that the distribution is essentially Gaussian, regardless of the speed in which I drive my system from the metallic to the insulating phase, turning on the electric bias. But when, depending on how much fast or how much slow I drive my system, my distribution gains an asymmetry, which is well captured by the skewness of the distribution. And on the other limit for strongly very deep into the Mott insulating phase, now I have this peaked distribution. A few transitions are possible, but their weight is almost negligible. But when I sum up everything, I will see that the average work that I can extract from the system is essentially 0. But I didn't have the animation working here. But basically, if I continue doing this protocol at different speeds, I will always see the same distribution. And it also has some skewness depicting. Okay, so now I have the actual distributions to show you in different regimes. So here is the non-interacting, L equals 4. You see a lot of excitations showing in the work distribution, a spread distribution, Gaussian, already Gaussian for L equals weight, for 8, skewness. And in the strong coupling regime, I see this almost single peaked distribution localized in 0. You see that for U equals 0, the distribution changes its average value, right? And then, okay, these are the distributions. I can take a look into the moments, and we can take a look into the moments. So here, the darker the blue, the fastest I'm doing the protocol. So I'm close to the pseudo-quench, to instantaneous change in this electric field. And the more yellow the curves, the more quasi-adiabatic I am doing this protocol. And what we see is that as I increase the strength of the Coulomb repulsion, when I am in the Mott phase, the insulating phase, I can barely extract any work, regardless if I do this protocol very fast or adiabatically, and this happens for both L equals 4 and L equals 8. And then the second moment, I have a lot of fluctuations in the work distribution. And remember that this has been associated with the entropy produced. So I have a huge, massive fluctuations depicting up to the point in which my system starts to become insulated, which is more or less here in this region here. And then if I look into the skewness, what is quite interesting is that the skewness changes its sign when I am in the situation in which particles can actually move because I created this electrical bias. But here, as I start to insulate the system, and it can no longer sustain this kind of transport, this skewness changes its sign. So in some sense, this skewness is capturing this change in the phase that the system has. The forward moment behaves more or less as the second, so it's kind of boring, so we won't take care of it. And because I already told you that we are interested in addressing the entropy production, we also investigated in more detail what could be the ratio for the fluctuation dissipation theorem. So this is the ratio between the entropy production and the fluctuations of work multiplied by the temperature I am at. And we saw that we are expected to see this upper bounded, and we wanted to see how close to 1 this ratio would be. And we saw that the ratio is smaller than 1 as you are below the insulating phase, because you have massive fluctuations, but as you decrease the fluctuations, you expect to see a lot of entropy production showing up. And we quantified also the distance between the actual final state and what should be the equilibrium state at different temperatures. Remember that beta equals to J is when I actually could have a quantum critical point, because I'm at a temperature equals 0. And this, you can see that if I am close to the ground state, the distance between the equilibrium state and the final state is huge. But as I increase the temperature more and more, the distance between the equilibrium state and the final state is smaller, because of course my distribution will be already almost like a Gaussian, and everything is balancing everything. So I kind of have more or less, I already started in an infinite temperature state, so it's very likely that I'll still be in this regime. Okay, so this was more or less this first investigation of the work distribution at finite time, making some sort of protocol for your system to kind of create some sort of current, and then seeing what happens when 2 different energy scales compete with each other at finite time. What are the consequences for the work distribution, the amount of work that you can extract, the work fluctuations, and the entropy production. We wanted to further investigate this business of the skewness, and what would be responsible for this skewness? This was the question we wanted to address. Was it because of the finite time drive? Was a particular feature of that specific model Hamiltonian? So we wanted to further investigate this question. And as I already showed you, we can separate well-behaved work distributions in basically 2 limits. I know that if I start my system in a given initial quantum state, I drive it at finite time, and then I drive it at finite time, but I do it almost immediately in a pseudo-quench regime. I'm expected to observe work distributions that are essentially Gaussian. Why so? Because I started from the ground state. I immediately shake the Hamiltonian. This ground state will scatter across all the eigenstates of the final Hamiltonian. It's kind of a change, instantaneous changes of bases. And this will be reflected in the work distribution, because of course, the amplitude, the probability for me to transit to states which are closer in energy is much larger than for me to go from this initial state to high excited states. And this is more or less what I expect to see if I just quench the system, change a given parameter instantaneously, and then this will reflect in the work distribution this way. If I go on the opposite limit, I do this protocol finite time, but very slowly, almost adiabatically. If I start, let's say, from a ground state or any excited state, I'm very likely to stay in the same state, because this state will evolve, this state will get upmost a global phase. And then what is going to happen with my work distribution? It will have a single peak, but this peak will change its energy depending on how far, depending on how I drive the system across this critical point, meaning that if I start from a ground state with a given energy and arrive to another ground state with another energy, the work penalty that I will inject in the system or extract from the system will be just the difference between these two ground states. Of course, this will be the result for non-critical systems, because if I am in the thermodynamic limit, when I have gaps closing, I'm not expected to see a single peaked work distribution. But in the middle, we just saw that happening, that the distribution for short times is Gaussian. But as I increase the speed, the duration of my drive, the distribution acquires a skewness as an asymmetry, up to a point in which it gets back to the adiabatic limit of a single peaked distribution. So the questions we asked were two. The first one, what's causing this skewness is just the fact that the external drive is carried out at finite time. But we also wanted, because we already know that in the two limits, my distribution is Gaussian, and say that the single peaked is a Gaussian as well, but without any fluctuations. We wanted to quantify how much non-Gaussian was my distribution depending on the speed of the drive, in a way to do what? To identify time scale separating the regimes in which I could describe my system within the sudden quantity approximation or the adiabatic approximation. So basically looking into the skewness and some sort of measure of non-Gaussianity, I would be able to tell you where any of these two approximations will work reasonably well, and even look into difficulties in building quantum controls for finite time drives, for finite time processes, for instance, shortcuts to adiabaticity. Okay, so I already told you that the main object is the skewness, and for this we have to study the work distribution. So say the skewness, the third moment, and the kurtosis will be two quantifiers for me to address how non-Gaussian I am. But also another quantity that Gabriel Landi pointed out was the negentropy, which is this nice quantity which was inspired in information in a measure of distance between two distributions provided from information theory. And basically the negentropy will tells us how far my actual distribution, this object here, is from a distribution that is a Gaussian with the same average and the same variance. So basically I get my work distribution, the actual one, the one that I just computed. I compute the average and the variance. I build a Gaussian from it. I create an approximate. I can even tweak this approximated distribution to include high order moments, and this was an approximation that we can basically from the Gaussian include the skewness and the kurtosis. Of course, I can iterate this with a more high order Hermitian polynomials to get a much better approximation for my distribution. But then I can compare these two distributions in a way to say how non-Gaussian my actual distribution is. And we had to select a model to investigate this business of the skewness and the negentropy, and we choose a very well studied model which also is featured in tons of papers in quantum thermodynamics, heat engines, quantum control, and so on and so forth, which is the transverse Ising chain. Here I basically have spins, a chain of spins interacting with the first neighbors in the z direction, meaning that if they are aligned, they like each other, you get a minus in energy. If they are disaligned, you get a minus in energy. And you can drive the transverse, a transverse field in the z direction. in such a way to go from a ferromagnetic phase in which all the spins of the chain are aligned, it could be up or down, to a paramagnetic phase at the critical point, which is basically where AH equals AAC equals to 1. You have the coexistence between two ground states, of course, if you start from the ground state. And the protocol you will be considering to study the dependency on the skewness and the negentropy on the speed of the drive is a protocol in which I start from a single ground state, in this case, the ferromagnetic phase. I drive my external transverse field through a linear ramp. That is, it's in which tau again controls the duration of the drive. When I am in the middle of this protocol, I'm crossing the critical point, and finally, when I finalize this the protocol, I'm expected to be in the paramagnetic phase if I do this protocol really slowly. And this model is also interesting because it displays the Keeble-Zurich mechanism, and one can show when you quench the system, you create a lot of magnetic imperfections, and the density of magnetic imperfections follows the Keeble-Zurich scaling. So this is a paper that is very interesting to look into. Okay, let's take a look at the results. So this is here I show you this protocol, which I start from the ferromagnetic, I cross the critical point in the middle of the dynamics. I can do this very fast. So this is the Sudden quench regime, and then I can do this protocol really slowly. And what I observe, that my distribution for the Sudden quench regime is Gaussian. This is a result for a spin chain of the size of 20, which is already huge. So okay, we included all the symmetries of the model, but this is the size of the Hilbert space is of the order of 20,000, so meaning that I have 20,000 squared distribution transitions showing here in the work distribution. And as when I started to do this protocol a bit slower, but let's say at time scales of the order of 1 in the units of all the typical time scales, which is scale with the h bar omega that I showed in the previous slide. So this is an intermediate time scale to drive the system, and as you go to the almost adiabatic regime, you see the distribution getting back to what we would expect. That is not, in this case, it's not single peaked, it's double peaked because the ground state is degenerate. So this is why we see 2 peaks with weights half. So this is the exact distribution. We see Gaussian, skewed, and then single peaked. And this is the approximated distribution that we built using the Gaussian plus the corrections with the skewness and the kurtosis. And then we can see that, yeah, it's really well captured. Say that this distribution is basically over. If you only have the first moment, the second moment, the skewness and the kurtosis, you have an amazing approximation for your actual work distribution. If you are capable of measuring these 4 moments, you are good in retrieving your distribution. We're looking into the moments, nothing interesting happened, so I will just skip and show you what is interesting, which is the skewness, in which we observe the following. So the skewness is almost constant where the distribution is Gaussian, right? It is still finite, it's non-zero, but it's finite, but it's almost constant. Independently of the system size, each color here shows a different system size. After a given time scale, it acquires a peak, meaning that your asymmetry gets really asymmetric towards the positive or the negative side of your average. And then after reaching this characteristic time scale, the skewness starts to drop and follows the power law. As we would expect, the larger the system size, the more retarded will be my time scale for me to observe this power law decay. And then negentropy shows a very similar behavior in which it's almost constant until a given time scale of the order of 1. It has a peak, well-marked peak between this characteristic time scale of 1 order of magnitude, and then it starts to drop and increase again. So we see that somehow these two quantities are equivalent, but in some sense, they tells us that in this region here, this time scale here, these are the time scales in which what I would expect to for my system to behave if I just quench it immediately, or if I do a very slow, almost in equilibrium protocol. These are the time scales in which I will struggle the most to describe what's going on with my system. Nonetheless, only having the first 4 moments is enough for me to be able to understand what's going on in my ability to extract or inject work for my system if I use the quantum work distribution as the main object to carry out this energetic analysis. Okay, so this is the non-Gaussian, and then now I will get to this very interesting following up work, which was, okay, so this is a many-body system. It has many degrees of freedom. All these degrees of freedom are evolving in a very complicated way. We know that many body systems have advantage, more is different, thermodynamically advantages, but what is responsible for this thermodynamical advantage? And we have this intuition that entanglement is regarded as a thermodynamical resource. So it was a natural question for us. Get back to all this investigation on the work statistics and connect with the entanglement. And the question we wanted to answer was the following. We know that all these many body systems, when we change a control parameter, we are basically changing their entanglement properties. How entanglement is connected with the moments of the work distribution? If it's connected, can we use the entanglement properties of the system, of these complicated many-body systems, to build a work protocol with an statistics that I want, with all the moments, the average, the fluctuations, and even the skewness? Can I control this using entanglement, all of them using entanglement? So this was the motivation for this following up investigation that we started a few years ago with Canella and Vivio. And as I already told you, one of the interesting things that I think the key point for us to start first asking this question is that, okay, we know that entanglement, this is well known, that entanglement depicts a discontinuity or a kink when I cross a critical point, and the same happens with the first 2 moments of the work distribution, as shown by Alessandro Silva in his paper, the seminal paper, Many-Body in Quantum Thermo, right? Then I can start asking myself, okay, there are different measurements of entanglement. I can, for instance, use the single site entanglement entropy. For instance, if I have a spin chain, it only tells me how much a single site is entangled with the rest of the chain. Or I can use the concurrence, which tells me how much a given spin is entangled with another spin of the chain, disregarding the rest. I can ask how these different measurements of entanglement are connected with the first and the second moment of my work distribution. And then I can revisit a phase diagram of a given many-body Hamiltonian in which can be built from entanglement instead of order parameters. Now I can think about building a phase diagram from entanglement measurements. And then I can start asking through that, how much work do I have to invest to go from a given phase to another phase? And how much entanglement does it cost for me to do a given transition, to have a given transition costing a given amount of energy? So you can revisit phase diagrams and entanglement and the energetic cost of crossing a given phase transition all together within this framework. And to address this question, we had to choose a model. We have chosen the superfluid to insulator fermionic transition. Why so? Because this particular fermionic transition has very interesting entanglement properties that can be captured through the linear entropy that I just showed you in the previous slide. And as a teaser, I will show you that what we are going to see is that we can build a protocol to actually absorb work into have work being absorbed in the system in such a way that when I minimize the entanglement of the initial state, I can actually store the maximum amount of work without any fluctuations. Okay, so this is again the Hubbard Hamiltonian, my favorite Hamiltonian from condensed matter physics. And now to describe the superfluid transition, the extra ingredient that I add to my original model is just point-like impurities across the chain. What is that? So imagine that you have your spin chain, the electrons, they can hop from one side to the other. I have the Coulomb repulsion or attraction in a given site, because I can control the sign of the U. And if I have U negative, my spins will love to be together in the same site. And this is what characterizes the superfluid transition, because you have this formation of pairs and your wave function behaves in this very delocalized way. But of course, if I add a given potential, say I will add a given potential V, I can kind of consider an extra penalty that if V is negative, my particle will also love to be in the site. But if I don't have V, it wouldn't like to be in that given site. So the competition between U now, the Coulomb attraction, and this point-like potential that has this meaning of impurities will be responsible for different phases. So if including the superfluid and the insulating. So if I have V negative, I mean, the particles will love to be in sites where V is. And U equals 0, I have the formation of pairs. So V localizes the particles, U negative enhances the formation of pairs. And because I can additionally control how many sites have these impurity potentials, I can play around with this phase diagram and ask myself, okay, how much work, what is a good work protocol for me to cross the superfluid to the insulator transition and connect that with the entanglement. And the entanglement properties of the superfluid to the insulator transition captured by the single site linear entropy, which basically tells us how much this a given particle of my chain is entangled with the rest is a really nice quantifier. Remember that I can add, I will call it disorder or impurity, in many sites of my chain. I can control how large or how small my V is. So I can control the disorder strength, and I can see how much, how it's like for the entanglement for me to cross this transition. I can also control the concentration of impurities. I mean, how many sites in which I put the V And then I can also look into the entanglement, and I can even change the density. I mean, how many particles I have in my chain. I can have a tensile chain and only 2 particles, and I can change both things. What is being seen is that you can cross the superfluid to the insulator transition regardless of the disorder strength. It only has to be after a given threshold that doesn't have to be large enough, but it has to compensate you, and then you enter the insulating phase. When you reach a given critical concentration of impurities, your entanglement vanishes. Why so? Because when you are precisely at the critical concentrations, your particles are localized. Those pairs which formed when you was large enough and created the superfluid phase no longer exist. The particles will localize. That's why I will have entanglement equals to 0. And then we can ask, okay, so if I start from a highly entangled initial state and then I do a protocol going, say, from the superfluid to the insulator or from the insulator to the superfluid, what happens with the work statistics? And then we started thinking about different protocols, quenching essentially 2 ingredients that drive this transition. I can, as I told you, increase the disorder strength, which will localize the particles very effectively, but I can also change the concentration of impurities. And here I show you 2 illustrations of these 2 situations. So increasing the disorder strength, meaning increasing V naught to VF, I can do this instantaneously, and I can change the concentration, say that I started with 2 sites with impurities, and then I can add an extra impurity. Of course, this, to be able to describe what's going on, I have to average over many different possibilities. So I have to consider all these possible permutations of impurities and what happens when I start from here and go to here, or if I start from here and go to here, and average of all in all these possibilities. And what we saw.
Sorry, Krissia, I'm really sorry to interrupt you. We're kind of a bit beyond time. If you want to have
Okay,
more
I
time
will
for
rush.
questions,
Okay, thank you.
but we have more time for questions and discussion, or if you want to go on, but then we will have less time.
I will just flush. Okay, so we show that in this protocol. No worries. Thank you for telling me. So yeah, so we considered this protocol for the Sudan quench, and what we showed was that the force moment was essentially associated with the single site entanglement. The work fluctuations were essentially associated with entanglement between 2 particles, and the skewness associated with entanglement between 2 particles. So in some sense, the work statistics can be controlled with this hierarchy of entanglement measurements, at least for the Sudan quench. So these I already show you in the previous slide. I will just flush. So again, we also look into the effects of the temperature. So here I start from the ground state, and we saw maximum work absorbed and minimal fluctuations. If I put a little bit of temperature, I will have thermal fluctuations competing with quantum fluctuations, and this will be responsible for me to increase the variance, the dissipation that I have in this protocol. If I increase the temperature large enough, I don't see any critical features anymore, and the amount of work, I can no longer inject work, I can only extract work, and the fluctuations will be massive. After my student, just to let you know, is working on the analysis of the time-dependent effects, and we are expect, because when entanglement builds up when I do a protocol at finite time, so if I do a reasonably slow protocol, I see a lot of fluctuations showing up, because now the entanglement becomes much more complicated. Okay, and just 1 minute, and then just to give you hope, and maybe Irene can give a talk about this. I do that. This is very complicated to handle. We have all these degrees of freedom, entanglement building up. Is there hope to simplify our approach to describe quantum thermodynamics of many body systems? Yes, there is hope, and the hope is from density functional theory, which is this nice toolkit from condensed matter, which allows you to map a many-body complicated system in an effective non-interacting system. And then we use this idea to basically build approximations for work and entropy. And then I will just flush because then you can tell this or I can give another seminar about it. But then I can show you that comparing the approximations with the actual result, we are very, very optimistic. And as a bonus, beyond being very effective to describe in a very cheaper way the thermodynamics of a complicated many-body system, the plus from density functional theory is that it allows us to describe these quantities as a function of the density. And these are quantities which are much easier to measure than, for instance, carry out a quantum state tomography, which is impossible for a many-body system, and retrieve the work distribution. Okay. So yeah, so this is more or less what I have to say. And just as a final message, I'm really happy to share with you all these thoughts on the studies of many body systems. There will be a roadmap being launched in a couple of weeks. Irene and Steve Campbell are editors of this roadmap. And we discussed a little bit of all the complications in studying many body systems, theoretically and experimentally. And yes, we need more people together to develop new methods and cheaper methods to study how do systems evolve, how we can manipulate entanglement to perform thermodynamic tasks. And on the other side, quantum thermodynamics can also help condensed matter physics to obtain smarter routes to assess phases of matter which are technologically important. For instance, the so wanted superconducting phase and high TC temperatures. So this is my message. With that, I would like to thank you all, and sorry for taking too much of the time, but yeah, thank you. I'm looking forward to answer any question.
Great. Thanks a lot, Krissia. Great talk. I personally have a lot of questions, but I will let the others ask first. If there is someone, please go ahead, or I will ask my question. So maybe I'll start. So one of the main problems of, I guess, modern quantum thermodynamics is how to characterize this probability distribution of work, right? On the classical case, it's kind of solved problem. We have a very powerful fluctuation theorem and allows to connect non-equilibrium quantities with equilibrium quantities, and we can measure them experimentally, more or less easily. In the quantum case, we rely on the two-point measurement scheme, which means that we measure in the energy basis before and after, so we make the system collapse the energy basis. So, for example, already there we have a problem. If you have entanglement or coherences, it might be destroyed in the process. And also we kind of need to know the state and the Hamiltonians. So we need to know kind of everything. I wonder, so in the first place, how you know that the entanglement of your many-body system actually influences the work statistics in your system, in your model.
And there was a recent work by Giacomo Guarnieri showing that at least in the linear response regime, you can retrieve the moments of the work statistics using quantities that are some sort of susceptibilities. And these susceptibilities are essentially the same quantities that are used to characterize order parameters. Essentially, they are connected with entanglement. So it's not directly entanglement, but indirectly what you are carrying capturing is some measurement of entanglement.
Great, thanks. So there is a question by Abel Kader saying, "Hello everyone. If you wanna say it yourself, go for it." And then there is Irene Damir. I might have heard you. No, am I wrong? Okay, so hello everyone. Thank you, Krissia, for this nice talk. I'm wondering if you have considered the case where the initial state has some quantum coherence, for example, by using the Kirkwood-Dirac quasi-probability.
This is a question I have been playing around for a few months now, and discussing with a few collaborators. I myself never considered, up to this point, I never considered the initial state with the coherences. But definitely, yeah. This is one of the perspectives for future work. Yes.
And then there is Irene, if you want to speak by yourself.
Sure. Hi, Krissia. Thank you for the very nice talk. So, in your comparison between the third moment of the work distribution and the negentropy, you had a figure, and the negentropy was showing a different behavior for longer times, if I remember correctly. I don't remember.
That's true. Yeah.
So there is this minimum. Could you comment on that, the difference with?
Yes. So if you are in the pseudo-quench, the distribution is almost Gaussian, so you are not expected to have a huge skewness. That's okay. As you go to the quasi-adiabatic regime, you have less fluctuations, right? Because you're almost adiabatic, so you're expected to see the skewness to decay because you are basically compressing the work distribution. That's fine. But then negentropy is measuring how far from a Gaussian you are. So in the beginning, you are Gaussian. So everything is corroborates the idea of the skewness. But when you are in the adiabatic regime, you are also compacting your distribution, but you are also getting back to a Gaussian.
Yes, but you have a minimum and then you go up again.
Yeah, the go up again is when you are here a Gaussian, then you skew and then you compress. When you compress, you are back to a Gaussian. That's why you increase, but here it saturates. It keeps constant after here.
Okay.
Yeah, only this kink that. So here you are very far away from a Gaussian.
Yeah.
Then here you are basically when you're localizing your distribution again, you almost get back to a Gaussian. Here you are still in a Gaussian, but you can have some fluctuation. Here in this model specifically, we can never have negentropy equals to 0 just because our ground state is degenerate. If we have a non-degenerate ground state, very likely that this negentropy will go to 0.
So the fact that you are growing again may be connected to that.
Yes.
Okay.
Because you have two Gaussians now, right? So, but you are comparing with a single Gaussian.
Yeah, sure.
Yeah.
Okay, thank you.
Thank you.
So there's another question in chat. Hello everyone, I am from NYC, I guess, your city, and my question is, will QEI come to NYC for us to TY the system? Thank you.
Yeah, I don't know if that's a real question.
I mean, we are a community, so I don't know who exactly will come to New York City and to do what system, but if you invite us, for sure, we will be glad to join. I might have another more broad question for Krissia. Like generally speaking, where do you see quantum thermodynamics or your system in particular as an application? Can be fully academic application, or can be something more valuable for society or technology. What do you think?
I looking into this perspective of identifying faster routes to phases of matter that are interesting, say superconductivity, I think this is the closest that we have to a technological application. But of course, just from the fundamental point of view, understanding the complication of very complex many-body systems, it can help us to identify easier routes to manipulate entanglement. And I think from the fundamental point of view, developing new strategies to simplify a complicated model and simplify actual protocols is something that in the long term can happen. But I think this business of combining condensed matter and quantum thermodynamics to reach given phases or anticipate is something that is interesting. But I also think that this idea of expressing thermodynamical quantities of complicated systems in an effective way, for instance, using density functional theory, which is something that people in cold atoms can measure, is something that, at least from the point of view of quantum simulation, can be interesting as well.
Great, thanks a lot, amazing, and amazing talks. As I guess we can wrap it up here if there are no more questions. So thank everyone for participating, and this talk was recorded and will be available on YouTube. Stay tuned for the next seminar, which we haven't organized yet, but